Good evening, everybody, and welcome to our fourth night at the Observatory live stream. Before we begin, I'd like to thank our sponsor for tonight's program, which is Casey Cadinia Libraries, located in Melbourne's southeastern suburbs. It is one of Victoria's largest public library services, supporting a community of over 450,000 residents. Casey Cadinia Libraries promotes literacy to all members of the community and supports free access to information in all its forms. If you'd like to know more, visit ccl.vic.gov.au to find out about the huge range of free online programs for adults and kids in the summer events booklets, and libraries are now open. And now for our acknowledgement. While we are all joining this event from our own location, we would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Boon Wurrung people of the Southeast Kulin Nation. We would like to pay our respects to their elders, past, present and emerging, and to all First Nations communities joining us today.
Petra, sorry to interrupt you there, but you may not realise you've got yourself on mute.
My apologies, I do have myself on mute.
That's
Silly
all right.
me.
We'll play that little introduction clip again because you had a great spiel for us.
Fabulous, I will do. So ladies and gentlemen, boys and girls, on tonight's MBO Bright Lights live stream, we'll be presenting to you Venus, also known as the morning or evening star. Stars, what they are and how they live and die. Our sun, the giver of life. Aurora, some of you may know them as the northern or southern lights. Supernovae, that are the exploding stars. Quasars, very bright lights in our sky. Satellites, the objects that orbit in space. And light pollution, what it is and how we can reduce it. So sit back and relax and enjoy tonight's show. Well, have we got a dazzling show for you tonight? But before we get started, I need to introduce tonight's presenters. So I'd like to run through them all. Come on in. Hello, everybody. Welcome. So I'd like to begin. Hello. I'd like to begin with our first introduction of our presenter, Jamie. You can see her in the middle and the top there for us. Thanks, Jamie, for a wave. And next to her, to my right, is Neil. Hi, Neil, give a wave. Then just below me, we have Stuart. Hi, Stuart, give a wave. And next to him in the middle, we have Merv. Good evening, Merv. How are you? Hi. Then we have Andrew next to Merv. Hi, Andrew. And just below Andrew, we have Steve. Hi, Steve. How are you? Next to Steve to the left is Adam. Hi, Adam. And lucky last is Jackie. Hello, Jackie. Good evening.
All right, folks, to kick things off tonight, we've got a new promo video for Mount Burnett Observatory. Those of you who've been to our previous streams will remember Jamie's fascinating talks on the history of MBO, but we've compacted that down a little bit, and this is something that we can share around as a little promotion of MBO. So if you think this looks cool, then when we put it online as a separate file, share it with your friends as well. Mount Burnett Observatory is a community-run astronomical society in the Dandenong Ranges. We are completely volunteer-run and have over 500 members. We focus on community engagement, outreach, diversity, and helping our members to get the most out of their love of space and astronomy. The observatory was originally built by Monash University for students to do astronomical research, especially on variable stars whose brightness changes over time. Over the next 2 decades, the site was expanded and upgraded, but eventually took a back seat to modern giant internet-connected observatories around the world. In 2011, our 5 founding members reached an agreement with the landowners and took over the lease and established the society. Now, we run over 80 events each year, including members' nights, public viewings, and special events. We have several special interest groups including deep sky observing, radio astronomy, astrophotography, astro arts, and young observers. In 2020, we expanded our online presence and now host regular live streaming events. We welcome all new members and love making new friends with other astronomy lovers. You will be joining a friendly community of passionate, hard-working amateurs who have a grand vision for the future of the observatory. We hope to see you up at MBO soon.
Yes, we do hope to see you up at MBO soon. But right now, I'm going to pass you over to Jamie, and she's going to talk about the Earth and the stars. Thanks, Jamie.
All right, thanks for that, Petra. So as Petra just said, I'm going to be telling you a bit more about the Earth and the stars. So just to kick things off, what am I talking about when I say stars? So stars are giant balls of hydrogen gas, and they're powered by a process called fusion. So this is where energy is being used to fuse smaller elements, namely hydrogen, into larger elements such as helium and lithium. So moving up the periodic table with time and this process called fusion. So the process of fusion also produces energy. Some of it is used to continue fusing hydrogen into helium and helium into lithium and so on. And some of it is released as heat and light. And as an example of a star, our sun is actually the closest star to us as well. And it is the reason that we're here today, but we'll hear a little bit more about the sun later on. Now, stars have what's called a Goldilocks zone, as scientists refer to it. So it's a spot around a star where it's not too hot and it's not too cold. It's just right for a star to be able to support life on a planet that orbits in this zone. So Earth is in the Goldilocks zone of our sun, which means that it is at a temperature, or the planet itself is at a temperature where liquid water can be sustained, which means that we can have life on our planet, which is wonderful. So it also gives us an indication of where to search for other planets that may support life. Gives us a rough idea of where to look around each other stars to find possible planets that support life. So stars themselves are born in stellar nurseries. These are usually where stars have died, and they use the remnants of previous stars that were there in their formation. So when stars die, because they're made of large amounts of gas, they throw out all that gas when they die, and that gets spread out, and then gravity brings it all together and makes more giant balls of gas, which we call stars. And you can see all of these throughout the galaxy as well, but we'll hear a little bit more on that later on as well. So stars obviously have life cycles, much like everything else, and what happens to them throughout that life cycle depends on their size. So smaller stars like our sun are part of what we call the main sequence. So these stars burn through their hydrogen slowly and can last for many billions of years. So as I said, our sun is an example of one of these. And when a main sequence star uses up all of its oxygen, it swells up into a red giant and it starts to fuse helium instead of hydrogen. Our sun's got about another 5 billion years or so before that happens, so don't lose any sleep over it. And once a red giant uses up all of its helium, it collapses to form what's called a planetary nebula, as you can see on the right-hand side of the screen there. And you'll also notice a little bit of a dot in the middle there. That's called a white dwarf, and that's the core of the collapsed star. So that'll happen to our sun eventually once it's past its red giant stage as well, but nothing to worry about, as I said. So the larger stars, on the other hand, they burn a lot faster. Some of them burn through their supply of hydrogen within a few thousand years, which is relatively quick in astronomical terms. So these become red supergiants when their supply of hydrogen runs out. And like the main sequence stars, they fuse helium as well into lithium. And then once they run out of helium to fuse, they collapse and explode into supernova. But we'll be hearing more about those ones later on. But some supergiant stars are more massive than those ones. And so when they collapse, they form black holes. And you'll see in the bottom left-hand side there, there's actually the first photo of a black hole that was taken earlier this year, actually. So credit to NASA researchers for that. That was a significant breakthrough, which was very cool. So that pretty much sums it up for what a star is. I'm going to hand back over to Petra now. All yours.
Thanks, Jamie. Oh, by the way, how long until our sun becomes a red giant again?
As I said, Petra, we've got about another 5 billion years, so don't lose any sleep over it. So good.
Phew,
So
phew.
good.
Okay. Well, seeing that we have got time, let's jump into Andrew's spaceship and see what he has on for us.
Evening all, how are you going? Yes, we're going to head off to Venus tonight. If you have questions, please put them and we'll answer them later on. Big thanks to Redshift again for allowing us to use their software for all this. This is a view, it's actually tomorrow morning, but this is a view of our solar system around about now. A couple of things to mention quickly since last time. The Earth has moved on ahead of Mars, and we're now also in a position that Jupiter and Saturn are in a virtual straight line. So have a look later tonight after the broadcast and the sun's gone down. Look to the west and you should be able to see they're very close together. But on the 21st, they'll be exactly lined up, and Neil's talking about that later. I'm going to zoom in a little bit, and we're talking about Venus tonight. And this is how we're lined up at the moment. So here's the Earth around here, Venus out here. This is where Venus is the morning star, as it is at the moment. And when it's around this side of its orbit, it's the evening star, which will be later on next year. It takes a while. While we're moving around here, Venus keeps going ahead of us. It's moving faster around the sun. So it'll be a little while yet. But at the moment, as you can see, there's quite an angle. So Venus is reasonably high in the sky in the morning. If you get up early tomorrow morning, just before sunrise, you'll see Venus as a very bright light. The other thing is that because Venus is between us and the sun, it actually has phases. At the moment, if you can imagine, the sun is lighting up most of what we can see, but this edge here, we would see as dark. We'll see that later when we zoom in on Venus. As it goes further around, even though it'll be lit up more, it's further away and it's more in line with the sun. So over the next couple of months, Venus will be less visible in the morning as it gets lower and lower as the sun rises. Eventually, it'll be in line with the sun. We won't be able to see anything for a while, and then it will become the evening star. All right. The other thing we can talk about is the transit, because, of course, in this part of its orbit, Venus could actually get directly between the Earth and the sun. Now, because the plane of these, let's just see if I can, okay, there we are. If we take it over, because the plane of Venus's orbit isn't exactly the same as the Earth's, this only happens about every 100 years or so, but it just happened recently in 2004 and 2012, where we had Venus going right in front of the sun. In 2004, in fact, I was still teaching and we went out just after school finished, which was very convenient, and the sun was still out. And we set up our school telescope attached to a cardboard box with a bit of paper in it, and we projected an image into that cardboard box of the sun. Of course, it's very, very bad to look at the sun through a telescope directly. You project an image, it's much safer. I've got a couple of photos here that should be up there now for you to look at. The first one shows roughly the apparatus that projected image into a cardboard box so that it's shaded from the sun. And then we can see a little black dot on the disk of the sun, and that's Venus going across. The next one, it's a little bit better angle. That square at the bottom is just the sunlight coming in, but you can see the black dot on the sun's globe. That's Venus. In fact, it was fairly early. It was about 4 in the afternoon in June. So, you know, the sun was coming down soon. Around other parts of the world, they would have seen Venus going right across the sun completely. Then it happened again in 2012. And this is what happens. They're about 8 years apart, but then you've got to wait another 100 years before it happens again. There's some more photos there too, very quickly, that some of our other outreach people took. So you can have a quick look at those as well. And while they're up there, the transit of Venus, some of you may have heard of in another way, and that is that it's associated with Captain Cook, because back in 1768, Captain Cook and his crew and the scientists on board were headed to Tahiti because astronomers had been able to predict when the next transit of Venus took place. But to see it properly, you had to go to Tahiti. So he sailed to Tahiti, and it was either on the way there or on the way back. He tripped over the east coast of Australia. And sure enough, he said, oh, this is a nice looking place. Let's claim it for the Crown. And as a result of that, we now all speak English. Well, most of us. Okay, so if it wasn't for the transit of Venus, we could be speaking another different language, or Australia still might not be discovered, probably quite visible from a plane. Anyway, transit of Venus, very important. So let's just head back to Earth now. Okay, hold tight. It's very quick. There's our beautiful planet. Here's Australia. Now, it's dark there because you'll see below, I've set this for tomorrow morning at 5:13. About 5:30, 6 o'clock, the sun comes up. Let's just swing this around to the east. The sun comes up in the east. Sure, there it is. The sun's just below the horizon. Mercury too. It's too close to the sun to see at the moment, but there's Venus. All right. You'll be able to see it very clearly because the moon is a beautiful crescent shape. All right. It'll be a crescent shape like that in this area. And then Venus will be a very bright light. As you go a little later, it'll get higher in the sky, so be patient. Hopefully it will be clear. It's looking very good at the moment, very promising. It's in fact the third brightest object in the sky. The sun is first, then the moon, but Venus is third. And at the moment, it should be very bright and very easy to see. If you want a closer look, you can have a look through a telescope or binoculars. Again, quite easy to see. At the moment, it's the morning star. So if you don't want to get up early, you'll have to wait a few months when it'll become the evening star, and then it'll be very plain. At the moment, it's about 1.5 astronomical units away, so a little over 220 million kilometres away. But when it's at its closest point in its orbit, it's only about 43 million kilometres away. So it's the closest planet to us. It's also the closest to us in its size. It's only just a little bit smaller than the Earth. If you went to Venus, and I doubt whether you'd want to, but if you did, you'd weigh a little less than you do on the Earth, not a lot different. So it's very similar to the Earth. Doesn't have a moon, doesn't have oceans, but more on that later. Let's just show you how Venus would look through a telescope. That should be flashed up on the screen. And you'll see that there's not much you can see, really. It's just a whole lot of lines and fogginess. That's because Venus is completely covered in cloud. That's why it's so bright. That cloud reflects so much of the sunlight, and that's what we get. It's close and it's bright So it looks a brilliant, brilliant star, hence its name, the goddess of beauty and love. It's a beautiful, beautiful thing in the sky. But thank goodness it's far away. It's got that cloud cover all of the time, ever since it was ever seen. It's through history. In fact, we didn't know very much about Venus at all, because even through the most powerful telescopes, there's no way we could see the surface. We didn't even know how long a day was on Venus. We knew how long it took to go around the sun. That's easy, of course, but we just couldn't tell anything else. We thought it would be pretty hot because, after all, it's the second closest planet to the sun, but they didn't have accurate figures. Then, through the space race, the Americans and the Russians in particular started sending space probes in the 60s, the 1960s. The Russians sent Venera spacecraft, the Americans sent Mariner spacecraft, and they all had a closer look at the planet. We started learning more about it. One thing we learnt is that it's a lot hotter than they thought. Temperatures are very, very high. More on that later. Then the Americans and the Russians tried to land a probe on the planet, and they found that was a little difficult. First, the space probe had to negotiate clouds. Well, they weren't water clouds. They were clouds of H2SO4, otherwise known as sulfuric acid. Not very nice. So that was the first problem. Then as they went down, they found that the temperature rose steadily until it was 450 degrees centigrade, enough to melt lead. None of the American space probes made it to the surface still operating, and it took the Russians a few goes, but eventually they were able to land Venera 9, and they were able to take this photograph, which hopefully you're seeing on your screens now. And it doesn't look a very nice place, very, very inhospitable. Flat rocks, no other features, just rocks, not even sandy surface, just hot, flattish rocks, very strong atmospheric pressure. In fact, it's like being a kilometre underwater on the Earth, so crushing atmospheric pressure. Very, very strong winds, and it was amazing that the Venera spacecraft operated as long as it did, and that was only a couple of hours. Of course, they haven't sent any more back to the surface. Better still, over the next 20 years or so, through the 70s, the 80s and the 90s, they were able to build up an actual picture of the surface by using radar scanning. So they had orbiting spacecraft which were scanning the surface, and they built up a detailed picture of the surface. And it looks like this, which hopefully you'll see on your screen. That's a radar image with enhanced colour. And it does, even in that image, it looks a very inhospitable planet. Anyway, let's go back to redshift now, and we'll have a closer look at Venus as it would be in the sky. Okay, let's centre it. And excuse me, that's not COVID. There we go. Here's Venus. Now, this is what I was talking about, the phase. This area of Venus will not be lit up. So if you look through a telescope or binoculars, you'll see a kind of almost oval shape, almost like just over a 3/4 moon shape. And as Venus progresses further ahead of us over the next month or two, it will become fuller, but it's lower in the sky, so hard to see. So it has phases. As Venus comes closer to the Earth in its orbit, we see less and less lit up. So you can even have a crescent Venus when it's fairly close to the Earth. It doesn't look very hospitable. Let's go and actually fly there quickly. And I won't take too long. Planets and moons. There we go. Let's go to Venus. So back down to the ground. Off we go. There's the sun going away closer to Venus. And here we are. Let's have a look around. And look at the surface features. There are volcanoes. There are very few actual impact craters. And remember, Venus doesn't have any moon to protect it from meteors and so on, but there are a few impact craters. But there's a few mountains, but they're not very high. They're fairly low mountains, if any. We've got areas like this. We've got sort of flat, featureless areas like this. It's possible because Venus's carbon dioxide atmosphere is like a super greenhouse effect. It traps huge amounts of heat. And scientists believe that every million years or so, the heat can't escape because of the blanket of atmosphere. So it builds up, and that areas of the crust, the surface, actually melt and reform. That way they can release more heat and Venus can form its crust again. So it's got a super greenhouse effect, and a very, very harsh planet, far from being a nice, what's the word? Venus is the goddess of love and beauty. It's not all that lovely and it's not all that beautiful. I certainly wouldn't want to go there. Recently, there was a new discovery just this year where scientists with very, very large, powerful telescopes were able to detect the presence of phosphine, which is a gas associated with living things. And a lot of hope was brought about because people thought, this phosphine is in much higher concentrations than would occur in just non-organic processes. And for quite a while this year, people believed that there must be things living in the upper, cooler part of the atmosphere of Venus, and that the phosphine was the indicator of that. However, I'm sorry, since then they've rechecked all their data, they've rechecked all their calculations, and they thought, no, it's not all that high. The phosphine levels are what you would normally associate with an atmosphere without living things. So sorry about the disappointment. Venus is not on the list of places where things might be living. So let's go back to Earth. There we go. Back to our beautiful planet. Goodness, we're here and not on Venus. Venus is not a nice place to be. Back to you, Petra. Thank you.
Thanks, Andrew. That was so informative. And next up, we have the news.
On the evening of December 21st, Jupiter and Saturn will be so close to each other in the sky that they will appear as one planet. Not since medieval times has such a close conjunction between the two been visible. At dusk, look very low on the horizon to the west to see for yourself. A pair of binoculars or a small telescope will reveal both planets.
Wow, isn't that great? Anyway, now we have Merv telling us about bright stars.
Hi Cosmos fans, it's Mervyn here, and I've just stopped along to bring you a little bit of information about some of those lovely bright stars you see in the night sky. Anyone stuck in the city will be familiar with a scene like this. Light pollution and surrounding trees, etc. will blank out most of the stars. I recommend you get away out into the country. Someone living out in the suburbs might get a better view of the night sky. But again, surrounding trees can block out a lot of the information, a lot of stuff out there. So get out further into the country. Okay, now you're away from the city lights and surrounding obstructions. Take a long look up. Stars will start to become better as your eyes get used to looking in the dark and start to notice the different colors. Away from all that pollution on a clear night and your eyes are adjusted to the night sky, you're probably looking at about 2,500 stars, maybe even 3,000 depending on the time of year. Wintertime more stars, summertime a little bit less, but you'll see the Milky Way stretching right across the night sky from beyond Orion down past the Crooks in the south. And this little view here shows some of the main stars. You'll start to notice too the different colors, reds, yellows, white, and maybe even some blue stars. So what do all these colors for the stars tell us? Most of the stars we see are in the yellow, white, and some blue. As I mentioned, the blue stars are usually quite massive. White stars are more massive than our sun. The other yellow stars in the night sky, similar to our sun. 70% of the stars that we see in the night sky are little, small, red or brown dwarfs. A few supergiants out there, and one or two hypergiants as well. Some of these we can't see with our naked eye, but the stars that we can see with our naked eye, let's have a little closer look at those. MBO members who are in possession of the Hot 100 things to see in the night sky might be familiar with this little list of stars. The information given here, mind you, is not in the Hot 100 list. There's about 20 stars visible naked eye listed in the Hot 100. These are the top 10. The stars marked in yellow here are visible in the southern hemisphere. You'll see one of the columns magnitude, and this gives the star's brightness. Originally, before the age of telescopes, brightness was measured, of course, by naked eye, and given the number 1 to 6. The brightest stars being 1, the dimmest stars being 6. With modern technology, of course, we can improve on those figures, and you see the numbers here. Anyone planning a journey to some of these stars, let's just take Canopus, for instance. Well, if you're traveling at the speed of light, it's going to take you 310 years. You're traveling in an Airbus, 281 million years. So, yeah, take a good book with you. Okay, now we're going to have a little look at some of these individual stars, especially the ones that you can see tonight, the ones marked in yellow. Okay, now you're getting a little bit used to looking at the night sky, and you're looking straight up, you can see the brightest star in the night sky. Around about 11 o'clock midnight, it's just about high. And this star is a binary star. It's part of the constellation Canis Majoris. It's roughly 8.6 light years away. Now think about this, if there's any 8-year-olds looking up at this star, you're looking at light that left this star when the year you were born. So it's arriving at your eye now, 8.6 light years away. It's a white star, it's twice the mass of our sun and almost twice the diameter. The more massive a star, the hotter it burns, so that's why it's a white star. The more massive a star, also the quicker it burns, so it doesn't burn as long as our sun will. Let's move on now to the next one, the second brightest star in the night sky. Okay, let's have a little look at Canopus. Now this star is much further away than Sirius. It's 310 light years away. It's 8 times the mass of our sun, and of course it's burning much hotter. The more mass in a star, the hotter it burns, and the faster it burns. This one with a temperature of 7,000 is in the constellation Carina. And what's next on our list? This little star right down at the bottom here in the south is Rigel Cantoris. I think about this one. It's one of the 2 pointer stars that point towards our Southern Cross. Rigel Cantoris is also known as Alpha Centauri. It's also a 3-star system. The 3 stars, one roughly the same as our sun, size and color. The second star is just a little bit smaller. It's actually a class K star. And the third one, Proxima Centauri, is the closest star to our solar system. But Rigel Cantoris, you can see here, the third largest star in the night sky. Okay, let's have a look at Rigel. This star is a blue star, in fact, a supergiant star. and it's part of the constellation of Orion. This star is 21 times the mass of our sun. So it's a pretty big star. It's got 79 times the radius of our sun. So it really is big. It's 860 light years away, which makes it a little bit dimmer than what you might expect. Imagine if the star was as close as Alpha Centauri, it would fill up the sky. Thankfully, it's quite far away. It's also part of a 4-star system, the main star being Rigel, the other stars being quite small. Well worth a good look. Okay, let's have a little look at number 8 on the list, Procyon. This star is a whiter. There's a white star. It's a bit hotter than our sun, and just about 1.5 times the size of our sun. It's in the constellation Canis Minor, and any 11-year-olds looking at this star, just think you're seeing starlight that left here the year you were born. It's 11.4 light years away, or 10.4 million years by your bus. So if you're planning a journey, take a good book. A little look at Achenar here, and this star helps us plot where due south is, drawing a line between the Southern Cross and Achenar, and about halfway between the two, we can drop a line straight down and find due south. The star is 69 light years away. It's almost 7 times the size or the mass of our sun, and over 7 times the radius of our sun. It's in the constellation Eridanus. It's also a binary star. And think about this. More than half the stars you look at in the night sky with your naked eye are actually binary or multiple star systems. Okay, let's have a look at Betelgeuse, or Betelgeuse, depends which side of the Atlantic you live on, how you pronounce it. This star is pretty amazing, one of my favorites. It's 643 light years away, so don't plan a journey soon. It is a massive red, in fact, it's a supergiant. Now, its mass, 6.5 times the mass of our sun, which doesn't sound that big compared to some of the other stars we've already looked at, but the radius of this star, 764 times the radius of our sun. So multiply that by 2, you've got one huge diameter star. And we can see it naked eye. It is part of the Orion constellation. In fact, it's Orion's shoulder. And this star, if we brought it to our solar system and put it where our sun is, it would actually take up the orbit of Mars. It is that big. So when you're looking up at Orion, just think about that, Betelgeuse. It is one huge star. Okay, last chart for my little presentation. You can see here the 7 brightest stars in the night sky with their constellations. I haven't put the name of the constellations in, it would have confused things a little. We can also see the planets here, so you can compare where the planets are when you go outside tonight. This is a view of what the night sky should look like about 10 o'clock this evening. So have fun, go out there and have a bit of stargazing. And many thanks to Stellarium for the use of their images. It's a free download for your computer and a couple of dollars for a download on your smartphone. An absolutely fantastic program, great learning. So go out and get it. And thank you very much for listening.
Thanks, Merv. That information was great. There sure are a lot of bright stars. Okay, next up we have Steve and his presentation about the sun.
Thanks very much, Petra. I'll just share my screen. Okay, so what I'm going to be doing is taking you on a brief tour of the closest star to Earth. So a lot of people sort of think that Alpha Centauri or Proxima Centauri are actually the closest stars to Earth, but that's not the case. The closest star to Earth is actually our sun. So just a word of warning before I start, and you probably know all this already, but never look directly at the sun. There are indirect ways to see the sun, but you have to be very, very careful and know exactly what you're doing. Otherwise, you are risking your eyesight. So, have you ever looked at a waterfall and wondered, as you watch the water tumbling down, where all the water came from? And of course, the answer is that the water came from rain. But imagine all of the energy needed to lift enough water into the atmosphere in order to keep all of the rivers and waterfalls of the world flowing each day. Imagine all of the energy that keeps the oceans from freezing over, the energy that powers the wind, that keeps plants growing, that circulates ocean currents around the entire planet, and which drives cloud formation, hurricanes, cyclones. And imagine all of that energy that has gone to keep our planet operating each day without fail for billions of years. So all the energy which governs how our planet operates comes from the closest star to us. It's a star we call the sun. Indeed, the forces which govern every object in the entire solar system all comes from the sun. And when you think about it, you may begin to wonder how much energy the sun must output each day for all this to happen. However, not many people thought about this prior to 1838. Now, before this time, the sun was instead thought of by many cultures as a god, and probably with good reason. But in 1838, a man called John Herschel became curious and decided to figure it out. And there's a picture of John Herschel there. So using only a can filled with water and a simple thermometer, he calculated that on a clear day and with the sun directly overhead, that about 1 kilowatt of energy is delivered to 1 square meter of the Earth's surface. Now, he knew that the Earth is 150 million kilometers away from the sun, so he imagined a giant sphere around the sun with a radius of 150 million kilometers. And by adding up each one of those kilowatts for every square meter of this imaginary sphere, he was able to estimate that the sun produced, now get this, 400 million watts of energy every second. Now, to put that into context, that's 1 million times the yearly energy output of the US, all in 1 second. And this has been going on for the past 5 billion years and will continue for billions of years to come. So what is the sun? The sun came to being from a vast cloud of hydrogen, which through gravitational attraction began to collapse in on itself over 5 billion years ago. And over time, this collapsing cloud of hydrogen became so dense that all the hydrogen atoms began to fuse together. And at that moment, that clump of hydrogen ignited in a process called nuclear fusion to become the sun. Now, the sun is basically a gigantic ball of hot plasma, about 1.4 million kilometers in diameter, or 109 times the diameter of the Earth. It expels vast amounts of charged particles and matter throughout the solar system at speeds of up to 400 kilometers a second. And this stream of particles is called the solar wind. The solar wind extends out about 18 billion kilometers from the sun before it is stopped by charged particles coming in from interstellar space. Now, this boundary marks the edge of a protective bubble around our solar system called the heliosphere, which protects us from cosmic radiation coming in from interstellar space. Now, the sun has a temperature of 15 million degrees centigrade at its core, but it's only 5,000 degrees centigrade at its visible surface, which is called the photosphere. And here you can see the white hot core, and this yellow area here is the photosphere. This is the visible surface of the sun that we can see. And the temperature difference results in huge convection columns, which continually transports material between the sun's interior and its visible surface. It resembles what you might see if you look down on a cauldron of boiling liquid. You can see the top of these convection columns, which are called granules, in this close-up of the sun's surface. You can see a sunspot here, but all this little mottled area is the granules that I was talking about. Now, above the photosphere is the chromosphere, which is the lowest part of the sun's atmosphere. It's only about 5,000 kilometers deep, and can only be seen during a total eclipse of the sun. So this is that orange area that you can see in the diagram. And above the chromosphere is the corona. You can see this streaming particles out here. That's the corona. And this can only be seen during a total eclipse of the sun as well. Now, if I can show you the next slide here, here's a photograph of an actual image of the corona taken during a total solar eclipse taken in the northwest United States in August 2017. You can see the moon there, and there's a few prominences, and all the streaming material is the corona. So it's only during an eclipse that you can see the sun's corona, which is one reason why many people travel the world to photograph and study them, because they're quite beautiful. Now, if you took a photo of the sun, and don't do this if you don't know what you're doing, you might expect it to be smooth and featureless. Indeed, over the last couple of years, it's been exactly that. However, the sun goes through a cycle of inactivity and activity every 11 years. And we are now just emerging from what is called the solar minimum, when the sun is relatively inactive and featureless. As it becomes more active, you start to see what are known as sunspots. The more sunspots there are, the more active is the sun. And in 5 years or so, we will reach solar maximum, where the daily sunspot count can be in excess of 200 sunspots. So this is a video of the sun that I took just last month over a 2-hour period, which shows a sunspot called AR2781. There it is there. Now, this is one of the first big sunspots that's coming out of the current solar cycle. And you could actually fit the Earth several times over in that little black dot. Now, sunspots are temporary phenomena and appear dark because of magnetic field fluctuations which inhibit convection and make the area cooler. They usually appear in pairs, and you can sort of see 2 pairs there. Each pair has an opposite magnetic polarity. So one has a positive charge and the other one has a negative charge. And if you look carefully at the video, you can see the development of a solar flare. This is sort of this white area. You can see it's you can't see it at the present time, but just wait, and all of a sudden it's coming. There we go, bang! This solar flare erupting on the surface of the sun. Now, a solar flare is an intense, abrupt release of energy that is built up between opposing magnetic fields in an active region. And as a result, you often see solar flares where there is sunspot activity. Sometimes a solar flare can trigger what is called a coronal mass ejection, or CME for short. Now, this is a huge bubble of gas which contains billions of tons of solar matter, which can be propagated on the solar wind. And if directed towards the Earth, a CME can trigger aurora and can interfere with electricity grids and telecommunication networks. Indeed, a CME hit the Earth's magnetic field just the other day, and it affected shortwave radio transmissions above South America for a short while. And the grainy surface that you can see here on the photosphere are the granules I was talking about previously. Now, there are over 2 million of these granules all over the sun's surface, and each of them are about 1,500 kilometers across. Here's another video. It's not a very good one, I'm afraid, but it's a video of a solar prominence, which is an eruption of gaseous material extending hundreds of thousands of kilometers up from the sun's surface. Now, prominences exist because of hot ionized gas, which clings to strong magnetic fields of the sun. So the gas traces out lines and loops where the magnetic field lines are present, much like what happens if you spread out iron filings on a sheet of paper with a magnet underneath. Now, for us, of course, the sun is everything, but the sun is just another ordinary star in a galaxy containing billions of stars. It occupies every aspect of our life, yet if you went out past the orbit of Pluto, it would look just like a bright star in the sky, just like any other star. And all stars have an expiry date. The image you can see is the famous Helix Nebula. In about 5 billion years from now, the sun's supply of hydrogen will become exhausted, and it will eventually swell up to become a red giant star, similar to Betelgeuse. All the inner planets, including the Earth, will be consumed, but as it expands, all of the sun's outer layers will be ejected into space, just like what you can see in this image. So it won't explode, but it will just gradually expel all these shells of gas out into the interstellar medium. Now, at the center of this image, just there, you can see the white hot core of the star that remains after all of its outer layers have been ejected. Now, this is called a white dwarf star, just there. Once our sun has ejected all its outer layers in this way, it too will become a white dwarf star. And there it will continue to exist for billions and billions of years to come. Our solar system will be unrecognizable. However, the material ejected into space will eventually become incorporated into new stars, and the cycle of birth and death and rebirth of stars will continue on. So thank you, and I'll just pass you back to Petra.
There we go. Thanks for that, Steve. That information was fantastic about our sun. How are those solar flares? They're just amazing. Okay, now for another 30-second news break.
The astronomy community worldwide is in mourning after the collapse of the iconic Arecibo Observatory. The huge radio telescope in Puerto Rico found the first evidence of neutron stars, participated in the SETI project, and transmitted the first deliberate interstellar message. Cables supporting the instruments broke in August and November, but complete collapse occurred on December 2nd. It will likely not be rebuilt.
Wow, what do you know? Anyway, right now we're going to have Adam.
Thanks, Petra. Well, welcome everybody. It's great to be here tonight, and I'm here to give you a short talk on some interesting facts about the aurora. Now, feel free to jump on social media. If you're on Facebook, hit follow so you get updates for when these live streams are coming up. And I always find it really fascinating to find out where you're all tuning in from. So jump on whatever social media you're using, give us a shout out. We've got an amazing team working behind the scenes, and I know they'll appreciate all the love that you're sending through. Most importantly, don't forget to ask questions along the way. We've got a prize later on to give away to the best question for the night. So keep those questions coming through. But hopefully, if we do this right, I shouldn't have too many questions left by the end of the night. So let's dive in. Bright lights. How can we talk about bright lights without mentioning the aurora? So what are they? Well, I just need to get my screen up for you all so you can see that. Hopefully you can see that. They're atmospheric disturbances. They can be really hard to see. There's different types and colours. It's a natural light display in the night sky. If you're wondering what they look like, this is one of the photos I've taken. I took this in Iceland back in 2016. And you can see the green colours of the aurora up in the sky. I actually couldn't see these when I was looking at the sky. I had no idea that they were actually there. I was actually just taking photos of the stars, and lo and behold, my camera picked this up, and it's quite amazing. Our eyes are not as sensitive as the equipment in modern day cameras, and yeah, I was absolutely stunned when I saw this. So these lights, they appear to move backwards and forwards, kind of like big sheets or curtains. They look like clouds just moving backwards and forwards. It's really quite stunning if you do get the opportunity to see them. They come in different colours, so they can be green, red, pink, purple, blue, and they're absolutely visually stunning. So where do they come from? Well, as Steve mentioned, they come predominantly from activity from our sun. So basically particles from the sun interacting with the Earth's atmosphere. Now, our sun's always releasing energy. However, some of these events generate a lot more energy than others. And as you can see here, they can be very, very, very strong and generate really strong aurora. We generally get struck by these particles, or the Earth travels into the path of these particles as we move around the sun. So as these particles collide with our atmosphere and these collisions fire off the light that we see in the sky, you might be wondering, okay, how does the energy from the sun actually create these amazing lights? Is there more to it than just these particles smashing into our planet from the sun? And that's absolutely right. There is a lot more to it, and it's all to do with the geology of our planet, or what's inside the planet. So if you think of the Earth kind of like a magnet, that really will help you to understand it. Now, it's really tricky because we think of magnets, it's an invisible force. We can't see it. And just in that video that you're watching, you can actually see these two magnets with opposing forces pushing each other away. However, they can attract too. So just like the sun and the earth, these forces are constantly sort of pulling and pushing. And we both have north and south poles. So it makes it a little bit easier when we look at magnets to sort of then relate that to the experience in our planet. Now we can actually observe this, and we can predict where these magnetic fields actually lie. And like Steve mentioned, if we drop some iron onto a sheet of paper with some magnets, we can actually then physically see where these field lines lie. And if you give the paper, as this video demonstrates, if you give the paper a bit of a shape, they start to take form. It's pretty amazing, isn't it? So if we take what we saw in that last video and we apply that to our star and the Earth, we can see this in action. And you'll probably start to notice, hey, that actually looks like those magnets we just saw, these magnetic fields between our planet and the sun. So you can see the Earth there. It's called the magnetosphere, that's generated by this iron core in the center of our Earth. An easy way to maybe think of this is if you look at those particles streaming in from the sun to our planet, you might think of them as sort of like electricity lines. So the energy from our sun is being transmitted along these big electricity lines, and they're striking the surface of the Earth. So how does that actually generate light and the electricity and this amazing aurora? And you can see it here. So if you think of the sun as the battery or a power source, it's constantly bombarding us with these particles and zapping our atmosphere. And you can see the aurora being generated in the north and the south right there. So another good question is, quite often people wonder, how do they get their colors? Well, it's all to do with the chemicals in our atmosphere. Now, our atmosphere is predominantly nitrogen and oxygen. That's what we need to breathe. How much we get zapped, or how much of that electricity is flowing from the sun, those particles interacting with our atmosphere, will also determine how bright or how strong and active the aurora are. And the height at which all this happens will determine what colors we see as well. So you can see here in this pictograph, it's really good representation of what we actually see when we're seeing the different colored aurora. So if we're looking down a little bit closer to the ground, around 100 kilometers in height, nitrogen particles will be lighting up purple. We can see a little bit higher up, nitrogen and oxygen generating blues and greens. And then we get oxygen all the way up the top, really bright red aurora. So do they only occur in the Northern Hemisphere? Well, no. So the aurora borealis are in the Northern Hemisphere, and they're also referred to as the Northern Lights. The aurora borealis, they're down south, and we can be lucky and see them down here if there's enough activity from our sun. It's quite difficult because of where we're located, but if they're strong enough, we've seen them as far as north as New South Wales, or even parts of outback Australia. Just to prove that they can be seen here, I took this photo down in Flinders. So they can be seen here if you look down to the south when there's lots of aurora activity or sun activity. You can see them, and it generates all sorts of different colors. You can see that this one in this particular photo, a bit of green very low to the horizon, but that pink and red extending up. So you might be thinking, how often do they occur? Well, they occur when our sun is active, and that probably then leads to the next question: is our sun ever inactive? And like Steve mentioned before, our sun goes through periods of when it's very active or not very active. And this is what it looks like. So you can see it's not very active in this image on the left, but on the right, you can see the difference when it is very active. So you would get more aurora as the sun is more active. Now, our sun goes through cycles, and generally it's over the course of about a decade, 10 years or so. So between 2010 2020, we've had our last cycle. So we peaked in about the 2014, 2015 years. However, lately, as you can see in that image there, it's been quite dormant the last few years. However, we're starting to see a few more flares occurring. So we're starting to come out of what's called solar minimum, and we're starting to move back into solar maximum. So we could expect to see more aurora occurring. So how long have they been occurring? Basically, since the sun and the earth have been around. Since we've had an atmosphere with oxygen and nitrogen, and since we've had that molten core spinning, generating that magnetic interaction between the sun and our planet. Now, we know the aurora have been around a long time because also throughout history, the northern lights and the southern lights have been featured through history in stories and myths. The very first time we discovered ancient evidence of the lights was through rock paintings discovered in southern France. These were painted by some of the earliest cave-dwelling ancestors and date back to about 30,000 years. Later, around 687 BC, the Chinese made the first written observations that we know of. So it's really fascinating. They've been around for such a long time. This is a snapshot of the aurora oval in the northern hemisphere. We also know that the lights feature heavily in Norse culture. Countries like Greenland, Iceland, Finland, Norway, because they're situated in a perfect position under that magnetic pole, they've been visible for thousands of years. The Vikings of Scandinavia believed that the Northern Lights were a bridge between the gods and Earth, and that bridge was named the Bifrost. Now, that name Bifrost might sound familiar. If you're a Marvel fan like me, it's for good reason. Does anybody out there watching, this is your chance to shine, jump in the comments, know which Marvel character used the Bifrost to jump between different worlds through the Marvel universe? I'll give you a few seconds. Maybe one of our amazing producers behind the scenes will pick out someone's answer and flash that up. And of course, it was Thor. Yes, well done, Joanne. There we go. So Thor travelled through the Bifrost. So I think it's amazing to see that connection between our history, our mythology, a real astronomical phenomenon that's been going on for thousands of years. And in a way, the Vikings had it absolutely right. The aurora is a visual bridge between our sky and the atmosphere. I think it's an amazing thing to be able to see that and know that it's been going on for so long. So the aurora only visible on our planet. Well, as you can see here, Mercury is the only one that misses out. Through all the amazing scientific equipment, we've been able to observe aurora on Venus, Mars, Jupiter, Uranus, Saturn, Neptune, and it's fascinating. We know that they exist, but we don't really know much more than that because we don't know what's inside these planets. If you look at Jupiter there, and we've also got one image coming up of Saturn, we only know where they're located. We can estimate their size and their strength. But other than that, we don't know a lot about what's inside these planets, unlike our own. So it makes it really, really mysterious in a way because, yeah, we don't know too much. And I think that's kind of cool because at the end of the day, it's fascinating. That mystery drives us to want to learn more. And if you do get the opportunity to see them, it's an experience you'll never forget. So that's all for now. Maybe next time we'll talk about ways to spot them and how to maybe photograph them. And yeah, that's all for me. I'm going to hand you back over to Petra. We'll see you a little bit later on.
Thanks for that, Adam. The auroras are very beautiful, and I'm sure many people would love to get a chance to see them. But up next, we have Jackie talking about supernovae.
Hello, my name is Jackie, and I'd like to talk to you about supernova, exploding stars that outshine the galaxies that they are in. Supernova are happening all the time throughout the universe. They don't just seem to be happening in our galaxy at the moment. This is a supernova right here, if you didn't recognise it. Stars need to be at least 8 times larger than our sun to go supernova, so our sun is far too small to explode, but it has another fate in store, which I'm not going to talk about tonight. And by the way, it's one supernova, but many supernovae. I also don't want to talk about the 7 different types of supernovae that are observed. And I don't want to talk about how the first type of supernova is used as what is known as a standard candle that is used to measure the distance of the galaxies that they occur in, as they always follow the same pattern of rising and falling in brightness. I could talk about the historical observations of supernovae, such as the famous event in 1054, which generated the Crab Nebula at the end of one of the horns of Taurus. That was widely seen around the world in many countries. There are also supernovae seen in 1572 by Tycho Brahe, 1604 by Kepler, and then more recently there was the one in 1987 out in our neighbour, the Large Magellanic Cloud. The incredible pressures that occur inside these events make some of the elements that we are familiar with in everyday life, such as the oxygen that we breathe, the aluminium and silicon in the dirt and in the Earth's crust, the sodium and the chlorine that goes together to make salt that we love to put in our food, and the calcium in our bones and the iron in our blood. So supernovae make all of those elements and more, and they scatter them throughout the galaxy as the remains of their explosions expand, where they mix with other clouds of gas and dust, and they eventually form new stars and planets. But I'm sure you already knew most of that, so I won't go into them in depth. What I really wanted to talk about was how long a supernova takes to happen. Explosions are quick and fast, right? Okay, so that happens and they blink out. Or do they? Let's think about this. Stars live for millions of years, sometimes billions. Yet could they really just disappear in a blink of an eye? The answer is most definitely no. Take a look at the bottom of the graph. It's measured in days. Days, okay? The shortest time it takes a star to die is at least 3 months. It's often much longer than that. While half a year might seem quick in stellar terms, it's still a lot longer than you might realise. So the next time you see a star suddenly disappear, it's more likely it's been covered by a cloud in the distance or set behind a hill or a tree that you can't see in the dark. Supernovae should occur regularly in our galaxy though. It's been a while since we've seen one, and many astronomers dream of living to see one light up our sky. So maybe one day, when we least expect it.
Thanks for that, Jackie. I'd hope to see one day too. All right, now for our breaking news.
After a 6-year journey to the asteroid Ryugu, the Japanese space probe Hayabusa 2 returned to Earth on Sunday. A capsule containing its precious cargo of subsurface rocks from the asteroid re-entered the atmosphere over northern South Australia. scientists say that the tiny 1 gram sample is enough to help answer questions about the early solar system, including the origin of Earth's water and possibly even the origin of life.
Wow, that was pretty cool. Up next is Stuart with quasars.
Hello, everyone. Yeah, so as you've seen, there's plenty of bright things in the night sky if you start looking. Yeah, we'll be talking about another one. But we usually think of brightness in terms of visual light, the light that we can see with our eyes. But we can also look, we start our journey today with radio, which works with similar principles. And so we found out we could look at the sky with radio waves and thought, why not see what it looks like with that instead and see if there's anything different. And they found that there were bright objects in radio waves, not visual waves, but radio waves. And so they thought, well, why don't we see what they are? These days, we've got pretty good technology, and in fact, in some situations, radio telescopes can see things more accurately than visual telescopes. But back in the day, it was a bit blurry, so we just kind of thought, all we knew was the object that's emitting radio waves is somewhere over there. And once they started looking, they found a lot of these sources that were emitting radio waves in the same way. So they thought we better investigate. So they looked a bit closer and eventually found that they were coming from these small, dim blue stars. They definitely wanted to learn more about those. So one of the most powerful tools that an astronomer can use is to break up the spectra of a star, the light spectra, which is basically splitting up the light that you get from a star and looking at all the different colors that it emits, the colors that it emits, the colors that it doesn't emit, and the strength of the brightness of these different colors. And at this point in time, we'd gotten pretty good at taking the spectra of stars to the point that we had produced these nice categories that stars went into. So we could look at any star and immediately put it into one of these spectral categories, and that would tell us what type of star it was. But we looked at these small, dim blue stars that were emitting radio waves, and their spectra didn't fit into any of the categories. They couldn't make any sense of these spectra. And so, was it even a star? No one really knew. So they came up with a name. Because it combined all that we knew at the time, that they're quasi-stellar, they look like stars, but they're not. We don't know. Well, we do now, but they also emit radio sources. But we later found out that there are actually many of these objects that don't emit radio sources. So they had their name changed to quasi-stellar object, or QSO. That's still a bit of a mouthful. So they shortened the name to quasar. And that's what we'll be looking into today. So eventually they did make sense of the spectra. The scientists realized that they could make sense of the spectra, but only under one condition, that this quasar was extremely far away. And I don't mean very far away, I mean extremely far away. So I'm not talking our local neighborhood of stars. No, it's much further than that. I'm not talking at the edge of our galaxy or in our neighboring galaxy local group. I'm not even talking that there's a million light years. I'm not even talking in our neighborhood of galactic clusters. Nope, much further. I'm not even talking on the very edge of our galactic supercluster or even our galactic filament. No, we're going straight out the level of the cosmic web, the largest structures in the universe. And we found that the quasar had to be right about there. Well, that was the first quasar we found the distance to. And the second quasar we measured the distance to was several times that again. So we're talking billions of light years, many billions of light years. These objects were extremely far away. And they were fairly dim. There's no quasar that can be seen with the naked eye or even with a decent amateur telescope. They're very dim, but the fact that we can see them at all means that they're extremely bright because they're so far away. If you added up the brightness of all the stars in our entire galaxy and put them together, a quasar wouldn't be quite that bright. It would be 100 times brighter. They are extremely bright objects spewing out energy. One thing that we could determine about these objects, apart from they're bright, is that we found that they some of them changed brightness. Some of them as quickly as a few hours they were bright and then they were a bit dimmer. And science is full of interesting logical deductions, and this is probably one of my favorites. Yeah, they measured how long it took to shift brightness, and there's a law of the universe that says you can't travel faster than the speed of light. Nothing travels faster than the speed of light. And we know how fast the speed of light is. And if we have a very, very large object, the light that we see from that object, the brightness, comes from the entire surface. The brightness is added from the entire surface. So if the object changed in brightness, say there, we would see that as a different brightness, but the light from the edge of the object would take a different amount of time to reach us. So the fact that the whole object was able to change brightness over a few hours means we could put a hard limit to how large this object could possibly be, which was a few light hours, which is comparable to the size of our solar system. So here's a fun fact. If you turn off a torch and it takes less than a few hours for the light bulb to turn off, then you can safely conclude that the light bulb in that torch is smaller than the solar system. It's a fun fact for you to know. Yeah. So what is a quasar? I've strung you along for long enough. What could be dense enough and emit so much energy? What could be extreme enough? Surprise, it's a black hole. They come up everywhere in the most extreme situations. Yep, I've tricked you all. I'm still talking about black holes. If you remember my last talk, I was talking a bit about black holes. In that talk, I was mostly referring to stellar black holes. A few times the mass of the sun. They're not too large compared to a galaxy or whatever, but these quasars were the first hint to a completely new class of black hole. And these were the supermassive black holes. Yes, scientists jumped straight over the category of massive black hole and just went straight to supermassive black hole because these are truly enormous. Millions of times the mass of the sun. The largest we found go up to 1 billion times the mass of the sun. There's really nothing that's compared to these in size and mass in the universe. And so you might be having a bit of a questioning thought. I said that these objects were incredibly bright, but isn't the defining feature of a black hole the fact that they don't let out light? Well, they don't let out light from within the event horizon, beyond the point of no return. Nothing can escape a black hole once it's entered, but there's plenty of stuff going on around the black hole that hasn't quite entered it. The most extreme place in the universe is probably inside the event horizon of a black hole, but the second most extreme environment in the universe is probably just outside the event horizon of a black hole. And so these supermassive black holes sometimes have accretion disks, swirling disks of gas and dust that smash into each other and are put under incredible extremes of environment and energy flying around everywhere. And some of it falls into the black hole, but black holes are actually really messy eaters. You can think of them like Cookie Monster, trying to grab everything, but it just goes everywhere. And for supermassive black holes, a large percentage of the material that's accreting around it, swirling inwards, just gets thrown around everywhere by the laws of gravity and ends up being shot out in these polar jets. And yeah, so you end up with a quasar being a supermassive black hole at the heart of a distant galaxy, shooting out these jets, and they're actually fairly thin jets. So that also helps explain why they're so bright. They're not shooting light out in all directions and wasting energy. They're focusing all their light in one specific direction. And so we see them as quasars because we're in line with that beam of light coming from the quasar. But if a quasar is off-center, then we wouldn't see it as such a bright light in the sky. We would see that we would call the galaxy an active galaxy because there's other signals that we can detect that tell us that something extreme is happening in that galaxy. But yeah, so quasars, they're quite extreme objects, some of the brightest objects in the entire universe, and we can see them across from the entire universe. But there's plenty of questions left to answer about them. Some of the most pressing is, well, is it because of the sort of galaxy that these quasars form, or could any galaxy form into a black hole? Do they just need some matter to start accreting around the black hole? And also, how big effect do these quasars have on the galaxy as a whole? And could our own galaxy in the distant future become a quasar as well, and become a shining light that can be seen from the other side of the universe? So yeah, that's my short talk on quasars. Hope I've piqued your interest. Thank you very much.
Thanks for that, Stuart. We're definitely seeing lots of colours tonight. Next up, we have Adam, Jamie, and Neil doing a roundtable about satellites.
Satellites are cool, huh?
Absolutely. They let us do lots of stuff, including what we're doing right now, which is wonderful.
Exactly. Fantastic. Okay, so I've just put a short clip together, very last minute, but it's amazing. There's so much out there. I've just started out with looking at the planet Earth directly and just all the objects that we have surrounding us. That's pretty incredible.
And these are things that we put up there deliberately, not necessarily the junk that's resulted from things colliding with each other or being dropped by rockets launching.
Yeah, exactly right. That's I guess there is part of that encapsulated in that. I did just hear recently that there was actually a booster, I think, from a Saturn V that was doing its trip out around the solar system, and it's actually due to come back and actually rejoin our orbit soon. So it's fascinating.
So why are we talking about satellites tonight in our theme of bright lights? Why are satellites bright lights?
That's a great question. Well, I guess it's from my point of view, the straightforward thing is that satellites are going to reflect sunlight. So it could be, I guess in one way it's useful for us because we've got all these amazing pieces of equipment and technology up there, which you're going to see shortly, like the James Webb Telescope that's going to go up soon. Really important for us to be able to capture information about other planets and do more studies. But it could be problematic in a way too, I guess. And Neil, as an astrophotographer, I think you'd be able to elaborate on that a little better.
Absolutely, yes. Satellites can be very bright lights in our photos, and they're not something that you really want. Just like having a contrail from an airplane going through your beautiful landscape photo, you don't really want a streak from a satellite going through your photos of the night sky. So we try to do what we can to avoid those, or use techniques called stacking, where we take multiple photos and we blend them together to remove the things that are in one photo but not in the others. And recently there's been a lot been a lot of controversy around the new Starlink satellite constellation being launched by SpaceX. They are launching 160 satellites at a time, and right now they have more satellites in their constellation than all the other satellites that have ever been launched so far. So we've doubled the number of satellites just in the last couple of years. And there has been concern from amateur and mostly professional astronomers that all these satellites passing through the images that their equipment takes can cause damage to those images, can mean that the data that they're hoping to collect can be affected by that. And so there's a lot of debate and discussion about that right now. And personally, I'm sort of sitting on the fence because I know that worldwide internet access will be an absolutely huge positive benefit for the Earth. But it's important that we take into account the knowledge that we gain from looking at the night sky and what we can do to minimize the impact on that.
Yeah, that's really good points. It's actually interesting. I don't know if you know, Neil, but some of the latest batches of Starlink satellites, I was really annoyed that I didn't get a chance to put that in this video, but they are actually adding non-reflective coatings and doing things to try and minimize that effect, because obviously, like yourself, there are professional astronomers in certain observatories that have had shocking problems trying to capture data over long durations, and perfectly timed. This is one of the Starlink batch launches going on right now, so it's it's definitely a bit of a problem. Jamie, have you had much experience through your observations with seeing satellites while you've been out looking at the night sky?
Not really. Being the outreach coordinator means that I've had quite a few questions about, oh, what's that like going really slowly across the sky there? And I usually just have a generic answer of, it's a satellite, because I don't really know much more beyond that. But I know that we can use satellites for a lot of different stuff. It's not just making artificial constellations and things, though. That's right, isn't it?
Yeah, absolutely. You can see in the video here, this is what the Starlink satellites look like immediately after they've been launched. They're still very close together and in low orbit, so they're very much more obvious. They stand out like a sore thumb. But over time, they have their orbit raised and they spread out more, so they don't look like a line anymore. But you'll see them more frequently passing across the night sky. So as Jamie alluded to, when we're doing our outreach, we will often see satellites not too long after sunset. Satellites are most visible just after sunset, and sorry, my camera's just turned off. I'll put that back on again. They're often most visible just after sunset and just before sunrise, because to see them, they need to reflect the light from the sun. And so if it's directly behind the Earth, then the Earth's shadow is on the satellite, and so we can't see them. And many of our events happen around dusk, so we will often have satellites passing over. Typically, they just look like dim to moderately bright stars, but occasionally we get a big one like the International Space Station pass over, and that looks really quite dramatic. And whenever that happens on an outreach event, we always try and be aware of it and make sure people can see that it's happening and tell them to, wave to the astronauts. It's always a bit of a thrill to think that you're looking up into space and seeing a vehicle that there are actually people inside of.
Yeah, absolutely. I think it even adds another element, because you'll probably be well aware there's a lot of astro art in that sort of category. Some of the things that you can do with cameras and satellites, capturing over certain periods of time with different effects and filters, you can get amazing imagery from. So there's a whole other sort of aspect of it that I find really fascinating as well.
So, Jamie, what do you find that it's like showing people the International Space Station at a public viewing night? Do you get a good response from that?
Oh, definitely. It's a bit of a trip, as you said. It's knowing that we're looking at people that are doing, all this advanced research and handling all this very advanced technology and all the rest of it. It's amazing. I can't really describe it any better way than that, but it's absolutely incredible. And people are generally very, very excited as soon as we say, the ISS is going to go over at such and such a time. It's usually a case of, quick, everybody, go out to a telescope. I have actually had a couple of people ask me before, can we see it through a telescope? And I think we did try. I think we had Liam, who's one of our young observers who's been in past live streams as well. I'm pretty sure he's chased it for a bit, but yeah, it was.
He has, and if
Yeah.
I can interrupt you there, he actually got it so that I could see it myself. So he'd already seen the ISS through a telescope, and he said, "Does anyone else want to have a go?" And so I grabbed the eyepiece and had a look, and I could actually see it. I mean, there's conspiracy theorists out there that say that, you know, we've never actually launched satellites and they're not real. Well, I saw the H shape of the main body and the solar panels of the International Space Station with my own eyes through a telescope. So it was really one of the highlight experiences in my amateur astronomy career.
Yeah, well, I can't say that I've had that. Unfortunately, I didn't get into the line for the telescope quickly enough when Liam was tracking it. So I'd definitely like to. I think I'll be recruiting him the next time it comes over and we're allowed to go back up there again. And yeah. And
just quickly as an aside before we wrap this segment up, in the next upcoming newsflash segment is a story about the latest developments from SpaceX. And the way that the space industry is currently developing at the moment, we are likely to see a whole lot more stuff going on up there. For better or worse, we are starting to become a spacefaring civilization. And I'm excited about that, but I hold in reserve my excitement a little bit based on how that might affect the night sky.
Yeah, definitely interesting stuff. Well, viewers, I think that's all for us. Don't forget to keep the questions coming because we do have a competition running. We're going to give away a planisphere at the end of the night for the person with the most interesting questions. So keep them coming. Who have we got next, Jamie?
I believe that's actually me again.
Sure
Adam.
is.
Thanks, guys, for sharing your round table with us all. Before we see you, Jamie, we're just going to have our final news flash.
SpaceX took a significant step forward in the development of their huge Starship with a high-altitude flight test. Prototype serial number 8 flew to 15 kilometers in altitude before executing a belly flop maneuver to return to the surface. As it approached its landing, it flipped on its end and crashed spectacularly. This was an expected result, and the lessons learned will be applied to the next prototype. SpaceX CEO Elon Musk blamed the rapid unscheduled disassembly on low pressure on a header tank and congratulated the SpaceX team.
All right, well, how about that flowing on quite nicely from our roundtable discussion? All right, so just going to take you through now a little bit about light pollution. So up until this point, we've talked to you about what the night sky has to offer. And the question now becomes, how long are we going to be able to see it for? So as the population is growing, obviously we're using more lights. And in that process, we're losing some of the most beautiful ones in our sky, some of which you've already seen tonight. So as for a definition of what light pollution is, it is defined as an unwanted or excessive amount of artificial light. While it is true that we need light in order to be able to see what we're doing or where we're going, high levels of light pollution, such as what we see in urban or suburban areas, such as the city that you can see here, affects negatively not only our health, but that of the wildlife around us as well. So human sleep cycles rely on light to determine when we sleep or when we awake and how deeply we sleep as well. If you're in a brighter room, you'll notice that you have a lower quality of sleep than what you do if you're in a darker room as well. So those that live in the city as well quite often have difficulty falling asleep, and to that end, they often have difficulty waking up on time as well. Even in less built up areas, so if you live in the suburbs where there's less houses and therefore less people and less light, a bright light suddenly turning on from your next door neighbour's front porch is less than welcome, as it can wake you up as well, which is not ideal. And it's not just us that's badly affected as well. We have quite a lot of nocturnal animals, especially here in Australia. And because of all the light pollution, it means that nights aren't as dark as they used to be. So those animals that are nocturnal and hunt at night, their hunting patterns have changed as a result of light pollution. And this means that it's harder for them to survive because it's harder for them to get food, which is not great. And birds are affected by this as well. They don't get to fly above these problems either. Quite a few species of birds use the lights at night, so the moon and the stars, to guide their migrations. And these birds are quite often disoriented by light pollution. And quite often we see birds flying into well-lit buildings at night because of the disorientation caused by light pollution. There's a couple of aspects of light pollution that if we address them, though, we can actually reduce the impact that light pollution has on not only ourselves, but the animals and wildlife around us. So these aspects are things like glare. So as you can see there, glare is the excessive brightness of lights. So you'll see in the bottom there in the middle, a bit of an idea of what glare actually is. So 40% of that goes up into the sky, which is not where we need it to go. We've got 10% of that light gives us glare, which is uncomfortable to our eyes. And we actually only use about 50% of the lights that we see on the street, which is a bit wasteful, if you ask me. We've got something called sky glow as well. You'll see in the bottom right-hand corner there, that's the brightness of the sky in built-up areas. So if you're in a less built-up area and you go and have a look at the city at night when it's a clear night, or even if it's cloudy, you'll notice that there's the sky above the city looks quite bright, and that's called sky glow. So if we use less lights, that reduces the sky glow as well. There's something called light trespass. So that's where light falls where it's not wanted or needed. And we've also got clutter, which is where light sources are grouped together in such a way that they're excessive and bright. So we use these aspects, we counteract these, we can reduce light pollution significantly. So using lights that are less bright, we can reduce how glary they are and how much disorientation and discomfort that causes. As I said before, if we use less lights in general, that reduces sky glow. If we use proper shields on street lights, that means that we can direct the light to be where we want and need it to be. And using spreading out the lights that we do use means that we are reducing clutter as well, which is also good news. So if we all play our part, we can keep looking at the stars and we can make sure that they're visible for those that come after us, and we can teach them new ways to light up their world as well. So we can keep everything the way it is now, which would be great, and we can keep looking at the stars.
Thanks for that, Jamie. And if we don't run or use too much electricity, it's also better for our other environmental factors as well.
That's a good point, Petra. If we're using less electricity, we're burning less coal as well, which is a lot better for the environment too, which is another important factor to consider.
Absolutely. Yes. Okay, well, that's it for our presentations this evening. Everyone has done such a wonderful job. I'd like to thank you all for viewing. I'll just hand you over to Neil now.
Hi folks, I hope you're enjoying this evening's stream. Coming up next, we've got your questions and answers, but before that, here are a few important messages. This series is made possible by a grant from Cardinia Shire Council. Thank you to the Council for that. This event is being held in partnership with KC Cardinia Libraries. The libraries are open again and are looking forward to seeing everyone. Don't forget, they are free and everyone is welcome. If you like what you see here and you'd like to see more, you can follow us on our social media accounts. You can see the addresses on your screen now, including Facebook, Instagram, and our website. If you love astronomy and think you'd enjoy being part of our community, you might want to consider becoming a member. Memberships are $50 per person and cheaper for families, and you can sign up on our website mbo.org.au. Don't forget, This is a monthly series, so if you'd like to be notified when the next stream is going live, then follow us on our Facebook, Mount Burnett Observatory Incorporated, and you'll get notifications when we create new events. And finally, I'd like to thank our incredible outreach team who put together this series. Now, let's hear your questions and get some answers.
Great, fabulous, thank you. Okay, so I'm just going into the questions that haven't been answered, and we're going to ask, Jamie, this one's for you first. Penn Island would like to know, is there a chance there are microorganisms that are living on the other planets?
Oh, absolutely. We've been having a look at quite a few exoplanets in the past. So that's planets that are outside our solar system. Looking in that habitable zone that I talked about in the stars and the Earth presentation at the start of the evening. So if you remember, the Goldilocks zone is that bit around a star where it's not too hot and it's not too cold. It's just the right temperature to sustain liquid water, which means that there could be life living on that planet. Now, we have been looking for, in the past, we've been looking for more developed life, I'm going to say. So that's life that's similar to us in a sense that they're larger and that we can see signs of them more easily. But at this point, we've scaled that back to microorganisms because it's more likely that we're going to find something that is a similar size to bacteria and has a similar resistance to temperature changes and things like that, similar to what bacteria has.
Okay, great. Thanks for that. The next question goes to Jackie. What is the biggest sunspot? And this was asked by Jim.
Yes, I was going to expand on that. The question, I need to actually rephrase the question because sunspots are constantly changing and growing and shrinking and they never stay still. So it's rather than what, it's when. When was the biggest sunspot that we've observed? And that would be back around about the 1950s when the sun was really, really active. At the beginning of the 20th century, it was quiet and it gradually picked up. The sun goes through 11-year cycle where it gets where it's very quiet and then it gets active and then it goes quiet again. So our sun is actually a variable star. It varies about 5% in brightness every 11 years. And so when it's really, really active, that's when we get the most sunspots. So the biggest one that was ever seen was around, it was actually coincided with the International Year of Geophysics, I think, and it would have been, would have swallowed up the Earth at least 100 times. And probably thinking, the picture I've seen of it, it would have lasted over a month because the middle part of the sun takes about a month to rotate once, and so they would have seen it go around at least once and come back the other time before it completely disappeared. So I know in recent times that's when the biggest ones were seen, round about then.
Okay, great, thanks.
Yep.
The next question is for Adam, and it's from Ruby, who is age 7. She wants to know, how can we see the auroras in person?
Oh, melts my heart. Love it. I love it, Ruby. I think it's a really hard one to answer, and it'll take a lot longer for us to explain than we have time for tonight. So maybe tune into our next night at the observatory, and I might be able to run you through that in a bit more detail. But it takes a lot of luck because our sun really needs to be very active. You need clear skies. You need to be in the right place on the planet at the right time. So it's really quite difficult. And then, like I said, with my photo, I couldn't even see it with my eyes. So sometimes you need some equipment to give you a hand. So I hope that's a very, very short answer. But tune in next time. We might talk about it a little bit more.
Great, thanks, Adam. Okay, so our next question is from Saxon, who is aged 7 as well. And the question is for Jamie. Why does a star need to be 8 times bigger than the sun to be a supernova? Or Jackie, if you like to answer that too, that would be great.
All right, well, I'll jump in quickly to start with, and then Jackie, feel free to elaborate after I've finished as well. So basically what happens when a star dies depends on its size or its mass. So a bigger star will have more mass in it, and when that star dies, it actually collapses in on itself, and then it explodes. Now, the more mass you have collapsing in on something, the bigger the explosion's going to be. So when a star like our sun explodes, it's a smaller explosion, and that's when you get something like the planetary nebula, like what Steve showed us with the Helix nebula. That's a planetary nebula, so that's one that our sun's going to make when that one dies. But a larger star, something like Betelgeuse or Betelgeuse, depending on how you want to pronounce it, that one's a more massive star, so that one has more stuff in it. So there's more gas and things inside that one. So that one's going to be a bigger explosion when it dies, and that one's going to create a supernova. And if you have ones that are even bigger than Betelgeuse, that one's going to collapse in on itself, and it's actually going to form a black hole. And Stuart has actually spoken about those ones in a previous stream as well. Jackie, did you want to add to that at all?
Yes, need to be very clear that our sun is not going to explode. It's just not going to do that. So it's going to puff into a red giant, but the bits that are going to remain, so it's going to like puff off about half of it to form the planetary nebula, but bits that's left in the middle is going to shrink back into itself and turn into a white dwarf, and it's going to put out lots of ultraviolet light to make the planetary nebula glow. But the bigger stars, they just because they have so much mass, they have a really catastrophic implosion. The supernova actually starts as a implosion. It collapses back in on itself, and then it rebounds all back out. But stars, our sun's actually a small star, and it just doesn't have enough mass to do that. It just doesn't do it. So it's bigger stars and above, and then the black hole ones are like really, really, really big stars. So the fate of a star really depends on its mass. And there's some stars that just do nothing, like the brown dwarfs. They just be brown dwarfs for their whole lives. Then they're pretty boring, unless you like brown dwarfs. Yeah.
Thanks, Jamie. Yeah, thanks, Jamie, and thanks, Jackie. Okay, this next question is for Stuart, and it's asked by Grace Langmead, and she wants to know, what is plasma?
Yeah, it's a bit of an exotic substance, but or maybe it's a normal substance, and everything you know is a exotic substance, because plasma is actually the most abundant material or state of matter in the universe, far superior to solid state, liquid and gas, because all of the stars of the universe are made out of plasma. It's very similar to a gas because it's superheated and flying everywhere, but it's so hot that the very atoms have kind of broken up, and there's a lot of electric charge flying around. So it's a bit more sticky than a gas, and so so gas is very free flowing. Plasma is a little less. It's a bit more viscous and very hot because it needs to rip the electrons away from the atoms, but still a lot less dense than liquid state. So it's another state of matter. Some say the fourth. Some say there are only 4, but it depends how you count states of matter, because when you get into extreme quantum mechanics and all that stuff, there's states coming out everywhere. But yeah, hope that answers the question.
Great, thank you. I'm just going to do 2 more questions and then we'll call it a night. The first one is for Merv, and it's by Janelle, and she would like to know, what's the smallest star?
Yeah, jolly good question, because most of us look at the sky and we see all the large stars, the giant stars, the yellow stars like our sun, but the smaller stars, we can't see them, not with our naked eye anyway. With telescopes, we can see some of the smaller stars, the red dwarfs and brown dwarfs. With huge telescopes, we can see more. With radio telescopes, we see a whole lot more. What's the smallest star known? I can't say what is the smallest star, but the smallest star known is a neutron star. Its name, well, it doesn't have a name. It's just got a long number, CXOUJ085, blah, blah, blah. It's got a long number name. It's 1.2 kilometers in diameter. I don't know what its mass is. I don't know where it is, but that is the smallest known star. Now, one of the smallest red dwarfs out there is in the, one of the smallest pulsars out there is in the Crab Nebula. It is the center of the Crab Nebula. So that pulsar is about 10 kilometers in diameter. So does that help you?
Great, thanks for that, Merv. Now, for our final question, and it goes to Adam, and there's actually two together because they're kind of related. They're from Louise Gardner and Sarah Martin, and they've written, did I read a real article that Europe is going to send a space claw up to space to catch and throw space junk into Earth's atmosphere to burn up when it enters? And then Sarah has written, surely they don't still work. How can they get rid of them?
That is a great question. It's a tricky one, tricky problem that a lot of very smart people all around the world are working on. And if I could share my screen, if we could pop that up there in a second. You were exactly right. The European Space Agency has been working on this problem for a while, and the mission to fix this problem is called Clean Space One, and it's going to forcibly deorbit satellites or space junk to safely burn up in our atmosphere. And it is kind of like a space claw. It's going to fire a net out to capture the space junk and safely bring it back into our atmosphere and take it out of harm's way. So you're exactly right. You did read that, and that's going to, I think, launch in about 2025, give or take, depending on how the space programs, their flexible time schedules and time frames with those missions. So, yeah, hope that answers your question.
Fabulous, great. Thanks for that, Adam. And now, would you also like to let our viewers know, Adam, who the winner is for the competition tonight?
Yeah, of course. I think that would have to go to Ruby. Ruby, great question about the Aurora. You are going to be the winner for tonight's prize. That's the planisphere, the Mount Burnett Observatory planisphere, and that's going to come to you in the mail very soon. Congratulations, well done. Great questions. Thank you, everyone, to all our other viewers for all those fantastic questions. It was a fantastic night. We really appreciate your participation.